The next focus of system engineering is on requirements engineering. Now, the development of a complete and accurate definition of system requirements is fundamental to project success, and it's a primary focus of early systems engineering effort, recognising, of course, that a complete description is not always possible and some iteration is required. The life cycle of the system we saw began with business needs, which were then translated into a large number of statements of requirement, which formed the basis of the logical design and are subsequently elaborated further to form the physical design. Now, these transitions from the business needs and requirements to the stakeholder needs and requirements to the system requirements are managed by a very formal process called requirements engineering. And its aim is to ensure that all the requirements have been included, which means that irrelevant requirements are excluded. It also focuses on the fact that we can't fix poor requirements by good design, so it invariably follows that rigorous development of requirements is absolutely essential if the acquisition is to be successful. Once the requirements have been collected, the system engineering process then focuses on deriving and decomposing these requirements down to the next level, in a process we'll see later is called requirements flowdown. This process requires elicitation, that is identifying the requirements, analysis of those requirements, definition, validation, and then management of the requirements. Requirements engineering ensures that a rigorous approach is taken, therefore, for the collection of a complete set of unambiguous requirements from the stakeholders so that the system development can begin. As part of requirements engineering, we'll see later requirements traceability is essential. We have two sorts of traceability, and both traceabilities allow us to be able to trace design decisions from any level to any other level. Design decisions that are traced from the system level down to the detailed design decision we call forward traceability. And similarly, any individual design decision must be able to be justified by being associated with at least one high-level requirement. We call that backward traceability. Now, this traceability is important since the customer has to be assured that all of their requirements can be traced forward into the design. And further, any part of the design that can't be traced back to a high-level requirement is probably unnecessary work, something for which the customer isn't prepared to pay. Traceability also supports configuration control. If we need to change a requirement for any reason, we can see where that requirement came from and what's the impact of the change. Support for requirements traceability is a feature of the top-down approach, and it provides a mechanism which can be guaranteed that the requirements can be satisfied at any stage. A bottom-up approach can't provide the same guarantee. System engineering maintains a life cycle focus. It focuses on the entire life cycle of the system and takes all of these considerations into account during any decision-making process. In the past, it's been way too common to consider design options only in the interests of the issues associated with its acquisition and to pay little attention to through-life support. It's proper for project managers and their teams to focus on acquisition, that is their role, and we want to make sure that we meet the stakeholder requirements, minimising cost and schedule. But a lack of consideration of whole-of-life issues can often lead to larger than expected costs during utilisation that are met from budgets that are generally inappropriate and insufficient to keep the system in service. A lifecycle focus requires us to focus then on the entire capability over its entire life cycle, not just the product during acquisition. The result is a focus on what's called lifecycle costs, or whole-of-life costs, and sometimes called the cost of ownership. As a very simple example, it's false economy to buy a cheaper car that has very high running costs, particularly if a slightly more expensive car can be acquired with much lower running costs, and therefore the much lower life cycle cost or a much lower total cost of ownership. We also mentioned that a focus of system engineering is system optimization and balance. As we discussed in a later module, it doesn't necessarily follow that the combination of optimised subsystems leads to an optimised system. It's not normally useful, therefore, to allow the designers of subsystems to optimise their part of the system in isolation of the system-level considerations. Consider, for example, the impact of incorporating an F1 engine in a small family car. The engine may be a great engine and optimised for performance, but it will destroy the remainder of the drivetrain, which has been designed for a much less powerful engine. Additionally, the F1 engine is capable of propelling the car far faster than is safe given its current suspension and brakes, and is much faster, of course, than even legal speed limits allow. It follows, therefore, that a number of subsystems may likely need to be suboptimal, or at least constrained in some manner, to allow their combination, that is the system, to be optimal. System engineering also recognises that the system must be designed with balance in mind. For example, we must balance system performance with other factors such as social, ethical, cultural and psychological effects, amongst many others. Again, system optimisation and balance is a byproduct of the top-down approach. They can't be guaranteed by bottom-up methods. System engineering aims to manage and integrate the efforts of a multitude of technical disciplines and specialties, and so a principal focus, therefore, is on that integration. It's rarely possible these days for a complicated system to be designed by a single discipline. Consider our aircraft. We have aeronautical engineers who may well have a major role in the design of the aircraft and be involved in its development and production. But lots of other engineering disciplines are required in electronics, electrical, software, safety, EMI/EMC, production, metallurgical, corrosion control, and many others. Of course, in systems terms, other engineering disciplines are required for testing and for logistics and maintenance support, as well as for the design and building of facilities such as runways, hangars, refuelling facilities, embarkation and disembarkation facilities, and so on. Other non-engineering disciplines are involved, such as marketing, finance, accounting, legal and environmental. In short, there could be hundreds, even thousands of engineers and members of other disciplines involved in the delivery of a single aircraft system. The aim of systems engineering is to define the tasks that could be completed by these disparate disciplines and specialties, and then to provide the management to integrate their efforts to produce the system that meets the user's needs. In modern system developments, this function is all the more important because of the complexity of the projects, their size, their contracting mechanisms, and the geographic dispersion of contractors and subcontractor personnel across the country and indeed across the world. And finally, management. System engineering clearly has a very important technical role and provides the essential methodologies for system development. But it's not just limited to technical issues, and it's not simply another system engineering process to be adopted. System engineering has a management and a technical role. Now, project management is responsible for ensuring the system is delivered on time and within budget, meeting the customer's expectations. The trade-offs and compromises implicit in those functions are informed by systems engineering. Additionally, the scope of the project is defined by the work breakdown structure, which is predominantly the result of systems engineering and requirements engineering. So systems engineering, requirements engineering and project management are inextricably linked. They go so well together, they're a team that actually developed the project. And these issues we'll discuss in much more detail in later modules. So in this presentation, we introduced systems engineering and describe some of its key tenets. In covering the description of the discipline, it would have become obvious that system engineering also has a number of considerable advantages. In the next presentation, therefore, we look at the relevance and the benefits of systems engineering. If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.